So hello students, all of you, welcome to this new semester and obviously this new course. As you can see, the Numerical Analysis and Computer Programming from the title under General Science category. GS 4353 is the course code, and from the title you can easily understand how much important this course is and how much the significance of this course might be in your engineering applications. And you know this, that by this time in this 21st century we cannot do anything without computation. Computer programming is beyond everything now we are dealing with. Once upon a time we were stuck with the calculator, but now we know that the calculator, the upgradation of this calculator is the computer, and that's why the computing task is done by the computer, and the repetitive task which is done by computer, using which we have introduced the programming to calculate, to save our time, to make less consumption of time, so that we can move faster and faster. And this is possible only in this modern century by dint of computer. And the computer programming is obviously based on some structural features, and of which the main thing is the numerical method and the analysis of this numerical computation. We call this as numerical analysis, which will be learned in theoretical manner. The two portions of this, you can see the numerical analysis and the computer programming, from which we will be learning the theoretical portion, the structural background of computation, the algorithm behind the computation, and using which methods the computer will be working, and how we will be using the computer to go according to the numerical analysis we'll be learning afterwards. The first portion, the theoretical portion, will be taken by me. I am Abu Zar Muhammad Minhazuddin Ahmed. However, how much time I will be able to support you, I don't know, but anyway, as much time as I can be with you, I will be trying to move through this particular topic, the numerical analysis, the theoretical portion, and the second portion will be taken by our another lecturer, Zihan Mahmoud Nahian. As you know, he will be taking the computer programming portion later on. So first, the theoretical portion, numerical analysis, about which I will have to give some introductory speech to you, as this is the first class. I will be trying to introduce the KPI form in front of you, so that we will be able to get some idea about what we'll be learning throughout this course. The course will be divided into two equal portions. The theoretical portions will be taken before the mid-semester exam, and the computer programming will be taken later on. As you can see from this KPI form, which will be updated in the next week, we'll be getting the hopefully will be getting the updated version of the KPI form, just because we are working on it. Just because according to the ABET manual, we are trying to reconstruct the KPI forms, where we'll be comprehensively explaining all the portions, how we will be dealing with, how we will be taking the course, how will be the question pattern, in particular what is our objective, what is the student's outcome of this course. All things will be included there accordingly, and for this we are taking time just because we are still working on it. So final copy hopefully will be getting by the next week, I hope. So the portion, therefore, you can see in this KPI form that the numerical analysis is involved. It will be taken by me, and the total 3 contact hours, therefore 1.5 will be taken by me, and the remaining portions will be taken by Jihan. Your Jihan sir. So the textbook I will be referring, there are many textbooks which you can follow but I will be particularly referring this particular book, that is the Numerical Methods for Engineers. You can collect it anywhere. The soft copy might also be available. You can buy it via online. And this is compulsory course. We'll be teaching using multimedia in this course. Obviously, as it is numerical method and computer programming, we must use the multimedia, that is, we must use the computer as well to explain different computer activities, along with the written form of numerical analysis, the basic structural philosophy behind each computation techniques. However, the quiz, we will be taking 4 quizzes, or more quizzes than that may be taken by us if possible. And all of these quizzes will be likely to be as surprise quizzes, so you'll have to prepare your lessons in all of the classes. In each class, after each class, you will have to be prepared. You have to be prepared for any quizzes which might appear in the next week, as you know. However, the course contents in an overview, I can say the course contents will be this one, and the specific objectives of this course are these things. As it is written, the student outcomes are AEK according to the Abbott criterion. You will be able to understand all these things when we'll be completing this the final copy of KPI according to the Abbott manual. However, the week plans are shown there. Today, the first class, I will be giving the introduction to numerical methods. Also, I will be explaining the concept of errors. We know something, the terminology error by something, but in numerical method, what the error signifies, we will be learning here. Also, we will be trying to learn the application of Taylor series and Maclaurin series as well. I think by this time you are acquainted with this particular topics by this time, but still then we will be approaching towards this to find something new, as the topic, the numerical method, is also new for us to introduce. So the next week, the second week, we'll be dealing with linear algebraic equations, graphical methods. Different rules are there, and obviously the eigenvalues and eigenvectors, we'll be learning something about that as well. And finally, the third week will be, and there is a possibility of taking quiz in this week as well. So you will have to prepare, although I have the 4 quizzes will be taken as a whole by 2 of our faculty members, and if we get more opportunities, we will be taking more quizzes as well. So advanced quiz we will be taking, that will be better for you, just because we'll be taking the best performance of you, as you know. However, the next week, the third week, we'll be dealing with interpolation and curve fitting, which is very important in every engineering aspect, as you can imagine. In the fourth week, we'll be trying to solve the regression problems in different types of regressions. We'll be learning there, and obviously the roots of equation will be there as well in the fourth week, and different methods of roots of equations will be taught in that particular week. In the fifth week, we'll be learning about partial differential equation, ordinary differential equation, ODE, PDE, which I think you have learned something about this in your mathematical courses by this time in the first year, but still then, as it is numerical method, which is quite different from the analytic method, which we'll learn one by one, day by day, how it differs from the analytical solutions or methods. So therefore, this ODE and PDE, we will be learning again how to solve those equations using the numerical techniques as well. And different methods are available for this differential equation solving. And finally, in the sixth week, we'll be likely to touch the ordinary differential equations, some remaining techniques which will be remaining after the fifth week. If possible, it is optional for us. If we get enough time, we'll be trying to learn this particular topic. And also we'll be learning the numerical integration, the Simpson's rule, the trapezoidal rule, Lombard quadrature, how these methods, these are the numerical methods, how accuracy can be obtained, higher accuracy can be achieved using these rules for numerical integration by increasing, you will be learning the increasing the number of segments, etc. And also you'll be learning the numerical differentiation as well. And for that there are different techniques, forward, backward, and central differences. So these all are the theoretical portion of numerical analysis, and there are much more things you can find out in numerical method and numerical analysis, based on which the computer will be learning the solutions. Not always the analytical solutions the computer deals with, but also the numerical analysis, the numerical techniques it deals with. And primarily the computer deals with numerical techniques, not the analytical one. The analytical techniques are used by we human beings, but the numerical techniques, as computer can go fast, move fast, that's why the analytical solutions are not recommended for the computer. And the basis of computer is numerical method. You will be learning this when we'll be moving further. So this was made according to the physical class schedule, the consulting hour, but for this particular pandemic situation, the lockdown is going on, as you know that. So there are no restrictions for you for any consulting hour to contact with me. Don't feel any hesitation to contact with me regarding any problem or any complexities if you face. So however, that was our KPI form. Now I think we can start our original content for our course, that is the numerical analysis and computer programming. So first, to start with, I will be focusing on the first topic, that is the introduction to numerical method. Introduction. So first, if we introduce the numerical method, what is numerical method and what? There is not a single numerical method, as you know. There are different numerical methods. To start with, what are the numerical methods, if I ask you? Okay, to explain the numerical methods, we will have to know the reason behind why these numerical methods are initiated or inaugurated for our solution, for our aiding our calculations. First of all, the techniques by which mathematical problems are formulated so that they can be solved with simple arithmetic operations. These are called the numerical methods. That is, we will not be going for any analytical solutions like, okay, I will have to think how I can solve this. Is there any technique? The intellectual properties of human being, we try to make any particular technique which implementation of which technique will solve this problem more easily. That is our main target for any solving any particular problem. That's why you know that there are different techniques like while solving differential equations, you might be trying for separable, whether it is separable variable or it is not separable variable. We will be targeting this thing, based on which we go for a particular approach. That is the analytical solution. But in numerical method, we say that no, we don't have to go for any complexities. Rather, we will be doing the repetitive task to solve any particular problem using the arithmetic operations like addition, subtraction, division, multiplication. Using these operations, we'll be trying to solve the problem, and that is numerical methods rather than any analytical approach. So for this particular thing, a possible scenario arises, that is the complexity, and that is what we have mentioned here. This may involve a large number of tedious calculations, and that's why thanks to the digital computers, just because the repetitive tasks, the infinite tasks are done by these computers, which we will not be able to do within a specific amount of time. That is the main reason why we are now approaching towards numerical methods, and thanks to the digital computers, why we will be learning here. When in our theoretical portions we will be solving some mathematical problems, you will be learning there how much iterations or how much steps we will have to complete, how many you will be asking these things. So there will be large amount of calculations in your note or answer script while you will be trying to solve the problems, and you will say how much time it will require, and how many times I will have to do this same thing again and again. And that is the task when you will be getting the rationale behind the computers, why these computers will be used for doing this particular task, the numerical methods. However, let's move to the next slide. To give example of the numerical method, first of all, I will be focusing on the Newton's second law of motion, which is where you are acquainted with this. No one of you are not acquainted with this thing. There is nobody. So I will be giving a simple problem solution here. F is equal to ma, that is the force equals to mass into acceleration. To describe this thing, I have introduced the bungee jumper problem. As you can see here, the bungee jumper problem. There are some initiatives in Hathijil. As you know, there might be around 20 more initiatives or projects are taken based on Hathijil, one of which is the bungee jumper in that particular region of Hathijil, to make the recreational spot and to make it more popular for the people. However, the bungee jumper problem, the problem is like the change in velocity is determined by the gravitational forces acting on the jumper versus the drag force. When you will be you are just set free from the from a high from a high elevation, then you will be just falling, what we call the free fall in the air. But although we say this is the free fall, you know this, that there is no free fall at all in this earth, just because there are airs around us. And that's why when we say, in simplicity, we have used in our physics or while solving the problems regarding physics in your intermediate level, you have used the equation like dv by dt equals to g. But now we will be again using an additional term, which is the resistance from the air. As you can see from the figure here in the right side, the right portion, whenever the people, this particular man is falling in the bungee jumper arrangement here, as you can see, the downward force due to gravity G is acting upon it, but also the upward force due to air resistance will be also acting upon it. That's why this force will also generate an additional acceleration, and the acceleration of which we can represent using this particular terminology that will be resisting. That's why it will be subtracted from this particular G, and this is the terminology where we have used the CD. CD is the drag coefficient of the air. V is the velocity. As much as the velocity is the dragging force multiplied by that, the resistance of air will be more increased accordingly, and that will be divided by m, the mass of the human being or the object what is falling from above. CD is the drag coefficient, m is the mass of the jumper, and g is the gravitational acceleration. So while solving this particular problem, if I ask you to solve this, what will be the value of v? How will you be solving this? Can you solve this? What will be the value of v from this particular differential equation? As you all must have solved the differential equations before. If I ask you to solve this is a very simple problem, at least well acquainted one for you. You know Newton's second law of motion. So if it is a very simple thing, let's go for the solution. Tell me what will be the solution of v. Can you tell me what will be the solution of v? If we just eliminate the differential term from there, v, can you solve this using integration? Can you say what will be the value of v here? I think obviously you can, but can you do it now? Okay, rather we see what will be the analytical solution in the next slide. So this will be the analytical solution. As you can see, dv by dt equals to g minus cd by m into v square. If we move to the analytical solution, the solution will be like that, and obviously there is a terminology, as you can see, tan hyperbolic, and within which there is root over gcd by m multiplied by t. This is the analytical solution. So if you go for the analytical solution, obviously you can solve from this particular solution. You can imagine, obviously this analytical solution is very tough tasks for everyone to solve. Rather, why don't we go for any numerical technique which is very easier, which we know already we know the technique, using which technique we can make approach and come to the solution. Obviously there is a issue, like there is an issue of accuracy which will be introduced from this new concept. But before that, just see this graph to explain the accuracy and the numerical technique. Before that, please focus on this particular graph. This is v in the y-axis, the velocity, and the time is in this axis. So if we put the values of t, time in the equation, analytical equation, as you can see here, and you will be getting for a particular mass, particular cd, all these things will be constant, and you will be obtaining the value of v as well. For t versus v versus t graph, you can obtain the original solution of this particular function if we know the value of m and cd, as you can see from here. So this is the analytical solution. And what might be the alternative? The alternative is the numerical solution, which we'll be learning here now. Now this is the numerical solution we'll be dealing with here. From this particular equation, dv by dt, which we can also write as del v by del t for a particular segment, small segment of velocity with the change of a small portion segment of time, that is del t, which is equals to vt I plus 1. I plus 1 means iteration of t plus 1 and minus vti. That is two particular portion, 2 points will be taken here, as you can see in this the figure in the right side, this is VTI and this is VTI plus 1. This is TI and this is TI plus 1. Say TI might be 1, TI plus 1 might be 2, or say TI might be say 2 and TI plus 1 might be 2.5 seconds. It is also possible. This means just iteration. I plus 1 doesn't mean that 1 second will be added to the time. If Ti is equals to 2 seconds, Ti plus 1, the next iteration might be only of 0.25 seconds segment. So Ti equals to, if it is 2, Ti plus 1 with 0.25 interval, it might be 2.25 seconds as well. I think you can understand. So for this particular t, the velocity Vti and the particular this Ti plus 1 time, this is Vti plus 1, this is the velocity, change of velocity. So we can write this thing as like this. If we assume this as a straight line, the function, if we assume this is going like a straight line, connecting the straight line in between these 2 points, then we can write the solution as this one. The slope, this is nothing but the slope of this particular straight line. And dv by dt, this is the equation from where we can obtain the Vti plus 1. The next iteration velocity can be obtained using the formula. From rearranging this particular equation, we can get dv by dt, this is this one, and multiplying this with this Ti plus 1 minus Ti, we can write this thing like that, and Vti will be added to this one. So from here, what we understand here, if we know the velocity at time I, Ti, and we know the interval Ti plus 1, then we can also obtain the value of velocity at Ti plus 1. If we assume this as a straight line, then we can obviously understand or evaluate the velocity at time t plus I plus 1. And this will be the solution in numerical techniques. Obviously this will result, or this will generate some errors, but you will get an approximate slope for sure. So as much as the interval is shortened, we will be getting the higher accuracy in general. So let's move to the next slide to see the accuracy of this particular assumption. If we use the exact solution which we have obtained in the last slide from the analytical solution, you can see the analytical solution is shown here in blue color, the exact solution, and the approximate solution, as you can see, as we have assumed this as a straight line. In each segment you can find a straight line, and that's why this will be resulting in some errors, which is the numerical error. And as much from what I was speaking in the last slide, that as much as you shorten the interval, the time interval, as much as you shorten this and increase the data points, so using the same linear approximation, although it is erroneous, but if you shorten the step size, it will obviously give you higher accuracy for a particular assumption. So from which you can easily understand from this particular graph. However, so this is nothing but the numerical solution. That is, we don't have to know any analytical solution. If we know the numerical value of the time, the previous time, the current time, the value of velocity in previous time, and from the assumption we are making here, that is the velocity, this is linearly varying from time to time, this will be giving you a result like this. Obviously this will be a solution no matter whether this is erroneous or not, the error is very high or less, it doesn't matter, but obviously this will give you some solution. That is the fact, and that is our main theme, the main concept in the numerical method or numerical technique. Now, this was an example. We will be learning in details throughout this course, so don't worry if you have find some complexities while understanding this. It will not matter, just because we'll be learning in details from now on. So why we will have to learn numerical methods? To start with this thing, I must say some examples, like say for example about the F equals to ma problem. The analytical solution is very tough to solve every time. Each particular problem needs new analytical solution might be required for solving each techniques. That's why we need more different techniques, different analytical solutions for each problem. And complex problems, there are many problems in the world for which we haven't discovered any analytical solutions yet. There are different types of there are many more examples of analytical solution problems which we haven't derived any analytical solutions or process yet. So that's why the numerical method obviously easier and comprehensive to apply, just because the same thing, the repetitive task, will have to be applied upon a particular equation to get through the solution, which will be obviously very close to the original solution. That's why and in our particular life we don't need the accurate solution all the time, and that's why we always omit the higher orders or more digits after decimal. We most of the time we omit these things, so that means we don't need the higher accuracy all the time, and all the time we are generating some error, we are ignoring some things, some portions. So up to which extent is our requirement that will be indicating how much accuracy will have to obtain from a particular solution. And that's why, as error is a very common thing in our problems, mathematical solutions, so that's why numerical methods is a very suitable one to approach with, where we don't have any analytical solution for any problem, or even we will not have to give pressure or stress in our brain, rather we'll have to focus or give stress on the computer to solve this thing. Analytical solutions can be derived for only a limited class of problems, and that is the thing I have just mentioned here. A broad spectrum of problems can be solved using numerical methods. Intelligently use commercially available computer programs. There are packages available for solving any types of mathematical problem or equation. As you know, to make your own customized program to tackle problems which packages cannot solve. You can also use the numerical methods if you find that there are no available packages as well, but you can use the numerical method or your own generated method to make the computer, compel the computer to do according to your intent to solve the particular solution, and bolster your understanding of mathematics as well. So this is why we will have to learn these in why we learn numerical methods as a whole. But there is particular reasons why we'll need to learn this in civil engineering as well, which will be I will be describing here now on. Why the numerical methods we'll have to learn. Not only that, why we'll have to learn this in civil engineering in particular. Now we'll be describing this. So now we move to the why do we need to learn this in civil engineering. Now this is the question for us. In exam, if I give you these questions to write down why do we need to learn this in civil engineering, you will have to give some examples, some sort of examples. Now I have given some examples here while describing the necessity for learning this in civil engineering, As we all know that in civil engineering we have 5 major divisions, namely environmental, water resource and transportation, structural engineering, and the geotechnical engineering. In all these fields, you must need the knowledge of numerical methods. This is a must, and obviously the computer programming as well in this new era of 21st century. We cannot expect anything without the knowledge. We cannot expect anything unless we have the knowledge of the numerical method and the computer programming. For mathematical modeling, as you can see, and expressing physical observations in mathematical terms, that we need the numerical methods in civil engineering. Interpolation, what you will have will be getting in almost every experimental sessionals. You will get the interpolation, and obviously in theoretical courses as well, which will be applied in calculating damage analysis. For example, I have given the damage analysis of concrete bridges, optimum speed on a freeway. For example, this is in transportation engineering with a given range of frictions, peak ground acceleration, and this is obviously related to structural or geotechnical engineering, the earthquake acceleration, estimation in emergency management. This is some sort of structural or the emergency management in transportation engineering aspect are there for these applications as well. In these cases, we need interpolations to predict the values. So there we need numerical methods. The interpolation itself, this is a numerical technique where we explain or we predict the values in between the ranges, just because we'll be learning when we'll be explaining the numerical methods application over interpolation. We'll be learning in details. Error analysis is used in comparing approximate values with true value while working with variable data sets. This error analysis, this will be our main focus for this particular class today. Error analysis is used in comparing approximate value with true value while working with variable data sets. If we find satisfactory results, the variations are very small according to our intent, then we'll say that this approximate result is satisfactory, so we can use that value. Taylor series, for example, today we'll be learning this again, is used in calculating beam deflection analysis. Although beam deflection will not be learning today, but Taylor series will be giving the introduction today. Beam deflection analysis will be our probably the final task in these theoretical portions, while we'll be applying the numerical differentiation technique for solving the deflection values and all other values to calculate ultimately the moment for beam. However, Gaussian elimination is used in determining accurate the ground coordinates on Earth using coordinates of satellites. As we all know, we use the geometrical properties or the mathematical conditions to calculate the geometrical formulas. You know that if there are two circles are there, that will be obviously intersecting in 2 points, or it might be touching 1 point as well. If there are 3 circles here, if I say 3 circles are there, if we say 3 circles are there, then it will be in 2-dimensional cases. 3 circles will be enough to get the exact position of any particular point. But while it is in 3-dimensional spaces, so we need not only a space, say for example this is the sphere, the Earth sphere, we are in a particular portion, this is our position, so there are different satellites which will be focusing in this particular point. So satellite will be getting signals like this will be getting signal like this. So in 3-dimensional coordinates we need at least a position is to be intersected or covered by at least 4 satellites, so that we can get the exact 3D coordinate of that particular portion on the globe. And that's why we will have to set the satellites all around the Earth in such a way that all the portion, every individual points, every individual position in the Earth must be covered at least by 4 satellites, so that we can exactly evaluate the coordinate of that particular point. And Google, what does Google do? Google satellite or Google map, it particularly they have set all the satellites in such a manner that so that every position's global positioning GPS, so that it can evaluate every position accurately in this manner. So what is the application of numerical method here? Obviously there is a application, there is an application of the numerical methods over there, because when we will be giving all the signals, the intersecting points, how we will be obtaining these intersecting points? There is no match for any other analytical solution for this unless we go for the numerical techniques. We will be solving the numerical techniques for solving linear equations in the next class. Also the polynomial problems will be solved, and this is nothing but the polynomial equation, set of polynomial equations which will be solved to get the exact position of any earth coordinate. So these are the mainly applications, some sort of examples why we need to learn this in civil engineering. You will be learning in every semester. In all other aspects you will be finding these numerical techniques for solving different problems in your civil engineering course. In this undergrad course, also the masters or higher abroad, if you go for higher degrees, the numerical techniques, this is a must. However, let's move to the next slide. It says model needs some mathematical procedures, the numerical methods. What we say, the numerical methods, there are some mathematical procedures where we'll have to apply the numerical techniques to solve this. This can be identified as it is shown there: differentiation, integration, differential equations, simultaneous linear equations, and all other things, as you can see here. Say mathematical procedures, if I say nonlinear equations. What we say nonlinear equations, the equations where the variables will have order not equals to 1. If the power of the variables is not equals to 1, anything other than the 1, the equations will be converted into a nonlinear equation, as we know. So these are the sort of equations, the examples, the parabola, you say circle, all these are nonlinear equations, and the nonlinear equations have a particular property. Why do we say this is nonlinear equation? Just because the graphical representation will give you the answer. The representation says that all these are nonlinear curves in the plotted graph, as you can see below. And the linear equations, what do we say? The equations for we say the equations for line, straight line, those will have the value power of variables will be 1, and those will be linear in properties, if we say. If we give the example of a linear equation as I was speaking, that is, this is the sort of example I can give, that the interpolation, although we'll be learning in details in the next classes gradually, but to give example of this, say the interpolation, several types of interpolations there: linear interpolation, polynomials, spline, trigonometric. Okay, most linear interpolation is the mostly used in civil engineering as for the simplicity of the interpolation, the feature, the attribute of this. interpolation, as you can see from here. What is linear interpolation? The linearity, assuming the linearity of the function in between the 2 points. The known value of the 2 points are x0, y0, x1, y1. The 2 coordinates are known. We'll have to evaluate for a particular value of x in between these two, what will be the value of y. So this prediction is made according to the technique which we call the interpolation, and whenever we are assuming the change of the function is linear in between these 2 points, then this is called the linear interpolation, and we obtain the value where, by assuming this is a straight line, and the slope of this particular straight line is used to predict the value of xy in between these 2 points, 2 known points. And this equation is well known to you as a straight line formula from the very early, very beginning of the intermediate lessons, but now we will be expanding this thing further in this particular course, not today. However, to give example, when the linear assumption was made just before we started into the necessity of numerical method, the first thing we have taught was the application, the Newton's second law. As we all know, we have seen that if analytical solution is taken, then the curve will be like something curved. Notice it is not the straight line will be getting, but whenever we have assumed the straight line assumptions, we have seen the value, the linear interpolation. When you will be assuming the function as a linear one, then the graphical representation will be like this, as it is shown here in the first figure. The second figure shows that if it is polynomial, then how the behavior of the graph will be for this. And this is obviously more smooth than the linear one, as we all know, and we will be getting more accurate results from this, no doubt about that. And when we'll be going for the spline, and that will be more smooth, no doubt about that. And you all know that spline interpolation, you'll be learning. If you don't know what is spline, you can go and search for it. Spline is giving us a more accurate solution than the polynomial as well, although this is also curved, but this is higher accuracy curve than the polynomial one. This will give you more accurate solution, no doubt about that. In general, there are some exceptions all the time. We'll be learning time by whenever we'll be studying particular cases that what are the exceptions, and then we'll be learning the exceptions. But in general, we can say this is linear, not very much accurate. Polynomial is more smooth, spline is more smooth, therefore more accurate, we can say. Now the mathematical procedure, how to make approach in curve fitting with regression. This is an example. So we know by this time, I think you know what is regression. Regression is nothing but to take a best fit curve or straight line, whatever we say. The prediction, a model will have to be generated when we have particular set of values, data are there. Then we will have to search for such a straight line model from which the sum of distance of all points, data points, will be minimal. The observed values will be minimal from the straight line. That is our target in regression, as you all know. So in regression, when you have learned to make regression, then you might have been given some data points, and from which you have made regression. But what about the real life problem? There will not be like what was the problem in your previous semester, like 5 or 6 data points. Not like that. In real life, you will have millions of data, and you will have to create a regression. You will have to create a model of using those particular data sets. So how will make approach? So there is no alternative to this unless we use any computer programs for solving this. But the basic procedure will be the similar thing as we have learned here. We will have to know the basic behind this, so that we can teach the computer about this algorithm, and the computer will be working accordingly. In the figure shown there, it has shown the polynomial regression. When we make polynomial regression, this is a best fit for polynomial. Exponential, the shape is like this, exponential. Logarithmic, this is a logarithmic fit. And while making regressions, we'll be always starting with the straight line. We'll be learning this further later on, but now I will have to say that whenever the regression might be polynomial, exponential, or logarithmic, or many other many other attributes of regressions are there, which will be the best fit that we'll have to determine. Best fit will have to be found, will have to be evaluated, and that's why we'll make approach for all possible regression values. We'll try for polynomial, we'll try for exponential, we'll try to find out where minimum value is obtained, minimum error is obtained, and that will be the best fit curve for particular regression. It may be the straight line, it may be polynomial, it may be exponential as well. But not always the higher accuracy only determine the accuracy or accurate model. Sometimes if not higher accuracy, but straight line regression may be the suitable one. In some cases will be learned when this will be these cases will govern later on. Okay. Characteristics of numerical computing. As you can see, some characteristics will be there in numerical computing, and the first one, if I want to say, that is the accuracy. The first and foremost thing, whenever from the basic concept of numerical method, we can know that there will be some errors generated from the numerical computing, as the numerical computing itself is an assumption. We are trying to reach close to the exact solution. So that's why accuracy is a big deal here. All numerical methods introduce errors, and that's why we need to calculate error, evaluate errors, and we will have to find out how the minimal error can be obtained, and that will govern, and that will indicate the best fit model for any particular problem. There are two types of errors, if I say in broader sense, that is those tools are the truncation errors and round-off errors. These two categories are there. We'll be learning about this thing here today in today's class. And another characteristic of numerical computing is the rate of convergence. How quickly we can arrive at a particular solution. As we know, that's why different numerical techniques are there. We will not have to stick into a particular numerical computing technique. In computing numerical methods as well, we'll find different types or techniques. But why? Just because of the rate of convergence. The proposal of different techniques will give different rate of convergence, how quickly you can arrive at a solution. It is because although we say that computer is can perform any task with infinite capability, but in reality the computer has some limitation or shortcomings as well, for which we can say that we cannot use the computer for very high time calculating. Sometimes it might you might see that you have given a task to the computer is just working as an infinite loop, but it cannot finish this off. It is just going for this. So therefore, for even the computer as well, rate of convergence is a big deal, and that's why we need to sort out the accuracy of different methods, so that we can evaluate how quickly we can arrive at a solution in different techniques, and the suitable one will be used for the suitable problems. Numerical stability, the stability of the answers, how much stable your answers will be, that is another big deal in numerical computing. In some cases you will see that some problems will not be some techniques will not work for universally or for all the problems. It cannot give the similar amount of stability of answers you will find. So therefore different techniques will have to introduce accordingly. And also the efficiency, computational burden, which I have already talked about while I was discussing about the rate of convergence of computer, just because whenever the computer will be performing its task, computational burden, you know that there is a particular limitation, the capacity of the computer, particular RAM, the speed, all these varies. So that's why we'll have to optimize our problem so that the computer also can go through a minimum amount of time to solve our problems. Now we'll be introducing the errors in numerical methods. I will not be discussing very details, just because I will have to give examples or mathematical problems I will have to show in front of you. That's why better I discuss less in theoretical portions, rather while I will be working out the math, then you will be able to understand, I think. Errors in numerical methods. The errors is the topic which we will be focusing here now. In numerical methods, approximations are used to express the exact mathematical operators. If we come to the very first example what we have given here, the Newton's second law, and we have seen that the analytical solution and the numerical solution, the results are varying, and the difference between the original solution and the approximate solution is called the error. And for this evaluating this error, how we will be quantifying these things, there are some terminologies we will be learning here, according to which we will be able to denote different errors, from where you can easily understand which error signifies which one. The true error, which is denoted by ET, this is nothing but the difference between true value minus the approximation. So if the true value in this particular point is, say for example, the particular point in this is 30, the true value, and the approximated value is 35, then what will be the true value? True value will be the true error will be the true value minus approximation, that will be 30 minus 35 equals to 5. So that's how the true error ET will be calculated. Then we come to the percent relative true error, and this is denoted as epsilon t. This is nothing but the true error according to, based on the true value. So if you say that okay, the true error is 5, it doesn't signify anything, just because you cannot consider, or you cannot determine the extent of this error unless we go for the percent relative true error, which will give you an indication that how much the percentage of error based on the true value of a particular problem, which will exactly signify more, which will give you more information about the error. And that is nothing but the true error, that is true value minus approximation divided by the true value multiplied by 100, which will give you the percent relative true error. And this is the condition based on which, in a particular problem, if you say that our target range of percent relative true error is less than this percent, and based on that particular percentage, we will be determining that up to which accuracy we will be going to get our desired result. If you say this is a very simple problem, I don't need very higher accuracy, then we don't have to waste our time beyond a particular problem to get higher accuracy, digits and digits after decimal. We don't have to do this. And if there are some problems we need higher accuracy, then we'll have to spend time after that. This is an obvious thing. So we'll have to determine for which problem we'll have to give how much effort. That will be dependent upon the percent relative true error. Most of the time we'll be giving examples while conducting math problems. We'll watch their how the percent relative true error or percent relative errors will govern for determining the results of different mathematical problems in numerical methods. Errors in numerical methods, again, to if I say if the problem cannot be analytically solved, the true value will not be known. As I have said that while discussing in the necessity of numerical methods, I have said that there are different problems where you cannot apply any analytical solutions. You cannot determine the analytical solution, in fact. So for that problems, how we will be determining the true value? As we don't know the true solution, the analytical solution will be giving the true solution, as we know that. But in such kind of problems where we cannot determine any exact solution or analytical solution from there, then in those cases, how to determine the error? So in those cases, we cannot determine the true value, and therefore we cannot determine true error or percent true error as well, just because all those terminology, as you can see, you will be needing the true value. Unless we get the true value, we cannot determine these two terminology. So what will be the judgment method of judgment for those particular problems? That's why we go for the another terminology that is nothing but the percent relative approximate error. This is the new terminology we introduce that is applicable for all other aspects, where even if we know the true value, there can also we apply the percent relative approximate error as well. And the problems where we cannot obtain the true value, there this will be applicable accordingly, obviously. So we normalize the error with approximate value. Numerical methods use an iterative approach. Iterative means as much as we will be increasing the iteration, or as much we divide the problem into higher segments, in generally speaking, that the accuracy of the result is possibly will be higher in those cases. So while judging these things, we will be introducing the approximate error to judge whether the increment of the iteration, the accuracy of the particular solution is extended up to which value, the amount we'll have to quantify those things based on the percent relative approximate error, and that is nothing but the epsilon a equals to current approximate error minus the previous approximation divided by the current approximation. Not necessarily that the increment of the segments is always governing here, but also if we go for the higher accuracy, higher terms are included. Say for example, in the infinite series like Taylor series or Maclaurin series, at most the term we will be including into our consideration, the higher accuracy is possibly will be getting, and that's why the previous approximation having less amount of terms and the higher accurate portion using the current approximation including new terms there will give you the current approximation. The difference between these two will be said as the approximate error, relative approximate error in general, and the percent relative approximate error will be obtaining that thing by dividing it with the current approximation as it is shown there and multiplying it with 100%. So remember one thing, when we are dealing with approximate error, then the approximate error will be equals to this one only, and when we will be using the relative approximate error, the relative approximate error will be this portion only. When we will be using the percent relative approximate error, then we will be multiplying 100% with that. So this is the concept. This thing also governs or also matches for the previous terms we have learned, that is the true error and percent relative true errors. And there will be relative true errors, another term as well, where we will not be multiplying this with 100%. Okay. In general, the approximate percent relative approximation error epsilon a is denoted by this formula, as we know, and we sometimes use absolute values for this, so that the negative or positive doesn't matter for this case, just because only the difference we need to obtain most of the times. So we can use absolute values sometimes. Continue computations until a stopping criterion is satisfied. This is the criterion. We will be saying that, okay, this is a particular problem. Say for example, if I give example of this, say this is a particular problem. Say this is the problem. Sorry, this is the problem, say for example. So if we move like this one, this one, this one, these are the iterations, say step sizes. And if we move for lower, if we divide it into segments, like say if we divide it into more smaller this pieces like this, so that we get a value in each of these points, we'll be getting these values in these points as well. So this is quite easy to understand, that as much we will increase the step size, the problem will be complex for us to solve, and also it will take higher times for the computer to compute these things, so that we need a particular set of boundary epsilon a, so that we will be in each step will be calculating that, okay, this was the first step, we have taken this particular segment size, and in the next step we will be taking the segment size as this one. Say the segment size will be like this. If I give example, this one is a step size, this is the 2 step size, that is the step size is half there. So we will be calculating approximate error, percent relative approximate error in these cases as well. We will see whether this criterion matches. If we say that this criterion is below 10 to the power minus 3%. So if the approximate error percentage relative approximate error is below 10 to the power minus 3%, then we will say this is okay. So if we find that using this step size our criteria satisfies, then we'll stop there and say that this is the answer using this step size. And if we find that no, the accuracy has not been met, the criterion has not satisfied, then we will be dividing this into further portions to get the more accurate results. So that is the use of this percent relative error. And from there is a criterion ES, we say this is a pre-specified tolerance level, and EA, the absolute value of EA, this is the obtained value which will be obtaining by taking different step size or different iteration for a particular problem. We'll have to see whether this stopping criterion, our obtained value, is less than this E epsilon S or not. If it is less than that, then we'll stick on that particular step and will not move further. We'll say this is the answer. And if we find that this is not satisfying this criteria, then we'll be moving further and further and further. This criteria is used, and how to quantify this. If we say indirectly that, if we say the epsilon S value, like if we want our results to be correct up to n significant figures, then the stopping criteria indirectly it can be proved, that is equals to 0.5 into 10 to the power 2 minus n%. That is this value will be correct up to, if the epsilon S equals to this one, then it will be correct up to n significant figures. So for example, if I give example of this, say I am saying that Okay, the previous approximation we have found that is the value is like 7.012345. This is the previous approximation in case of approximated result. While using true, then it might be the true value. However, in this case we are dealing with approximation. So the previous value is this one, and the approximated value, the current approximation will be finding like 7.012 then 534 something dot dot dot. So this current approximation is correct up to what significant figure? Say 1, 2, 3, up to this one. 1, 2, 3, 0, 1, 2, 0, 1, 2, and after that no match is there. So this is accurate up to 3 significant figures. So n equals to 3. So if we want to make any epsilon a or epsilon s which is correct up to 3 significant figures, then the epsilon s will be equals to what we calculate from this particular equation. We put 3 in this point and the value we'll be getting in percentage will be the stopping criteria for us, so that we will be getting the correct result up to 3 significant figures. And nevertheless, if we want our solution to be correct up to 2 significant figures, then eventually our criteria will become like this. Epsilon s will be then 0.5 multiplied by 10. N means 2 minus 2, that is 0 and 1. So our criteria will be 0.5% if we want our digits are significant up to 2 significant figures after decimal, after point. So then the criteria will be like this. So indirectly we can calculate how much accurate our calculation is with this value of epsilon s indirectly. So we will be getting the real life examples or practical examples while we will be conducting the math problems afterwards. So let's quantify, let's categorize 2 errors. Let's learn about 2 types of errors we have just mentioned. First one is the round-off errors, which is resulting due to the rounding of any value after decimal. This, as you all know, that there might be infinite number of digits after decimal, but whenever we say that okay, we are satisfied with up 2 or 3 digits after decimal, so we will round up there, then for this particular thing some errors will be generated, and that particular error will be called the round-off errors. And this kind of errors are generated in the quantities in such as pi, 1/3, which cannot be expressed by any fixed number of significant figures, and that's why round-off errors will arise. And even digital computers cannot represent some quantities exactly. This is the problem as well. So we must stick to some digits after decimal, and for that particular thing the round-off errors will be generated. Say, if I give a very simple example, is, so let's say a value is 7.234578. If we round it in as 235, then the error due to ignoring this thing will be generated. The error will be called the round-off error. This error will be called round off error. Okay. Truncation error. From the name you can understand the properties of this error. Truncation errors will generate when there are infinite number of terms in the series, but we will truncate the all other terms, keeping few. Then, due to this truncation, the errors which will be generated, we will call these the truncation error. What's the difference between truncation and round off? Round off is originally the value we will be getting, but due to rounding it off, the error will be generated. But the truncation error is actually it will be occur in any series where the higher order terms will be ignored, and due to this ignorance the errors will be generated, and that will be called truncation error. As you can see from the example, the sin x example, it is an infinite series. It can be expressed as infinite series as x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial, blah blah blah. From this we can truncate the higher order terms and approximate up to some term, say first term only x, up to second term x cubed by 3 factorial, and truncate all other values after that. So this will generate some errors due to ignorance of the higher orders. The errors that will be generated, we can calculate subtracting from the true value, that will be the truncation errors. Another example was what we have given in case of the Newton's second law, the bungee jumper problem. We have seen the example there. We have assumed it as a straight line. So as we have assumed it as a straight line, the higher order terms, the differentiation, due to this differentiation, this is actually not the linear term. Although we have assumed it as a straight line, but there are higher order terms existing there as well. As we have ignored all other terms, that's why that will also generate some truncation errors, which we have seen graphically before. So let's come to the Taylor series. You all know the Taylor series about this. It is an important series that is used in expressing logarithm trigonometric functions into algebraic functions. Application. First, if I say the Einstein first used Taylor series in explaining Brownian motion. One super common example, when you use small angles in physics. When you will be using small angles, if I give the example of simple pendulum, if you can remember, where we have assumed the sin x equals to x just because it was very small. But why it was not very much significantly higher error generated by this? Just because of the Taylor series. It will be acting good when the value is very small. We'll watch that the sin x will be approximately equals to x, and that will become true in case of the lower values of x. Also, the Taylor series is important to derive another series called Maclaurin series, and you know Maclaurin series is actually derived from the Taylor series. Taylor series is also important for approximation a value of a function, and in civil engineering Taylor series is used in the beam deflection analysis. However, we'll try to see some examples. First, if I say the Taylor series, the general form of the Taylor series is this. This is very well acquainted equation, as you know. And if we use the interval as h is the interval, then if we know the value of function at x, then using that function of x, we can evaluate the function of x plus h, and for that we might need to differentiate the function multiple times. Some example of Taylor series, using this Taylor series we obtain cos x, sin x, exponential e to the power x. All these series we obtained from this Taylor series. And the Maclaurin series. What is Maclaurin series? Actually, the Maclaurin series is nothing but this one. That is the epsilon e to the power x equals to 1 plus x squared by 2 factorial. This series is called the Maclaurin series in particular, which is another form which derives from the Taylor series. So you can easily derive the Maclaurin series from the Taylor series about the point 0. When you know the value of function at 0, then you can also equate the value of this function at x plus h, 0 plus h can be evaluated. And then you can easily calculate the values as this one. So that's how we have obtained the Maclaurin series. But that is not our concern in this particular course. Rather, we want to use this series, all this series, for calculating the error, the properties of error, the approximation criteria, whether it satisfies or not, comparing the analytical solution, true solution, with the approximate solutions here. So this is an example how to quantify truncation error. If we truncate, say for example, we know the value of function at point x, xi, say xi equals to 0, in that point we know this value. Okay, so the true solution will be this one, this curve you can see in this particular figure. This is the actual true solution. So in case of if xi plus 1, which is equals to 1, at that point the value of function will be actually this one, this particular point you can see there. But if we know the function value at point xi, so how to quantify the truncation error? Before that, how to approximate? If we take only the first one, if we truncate all other higher order terms from this particular series, then what you get? You know the value of function at point x, and you are assuming that function of xi plus 1 will be equals to function of x. That's why there will be no change. In 0th order, you will be getting the same value here, as you can see there. In first order, what will happen? You will be adding up function prime xi plus h. Don't think that this is going downward, so how it can go downward as we are adding this thing. This is just sort of not quantitative example, this is a qualitative example, so don't take like this. And also the function prime might be the negative result can be obtained from there as well. So we don't know the exact value whether it will be plus or minus. However, just take it qualitatively. Function prime x into multiplied by h. When you will be adding up this term as well, this says that the f prime x, this is the first order differentiation. That's why we say this is the first order, adding up the first order within this function in the Taylor series and truncate all other higher orders. That's why we'll be obtaining the value as this one, which is different from the previous 0 order value, and that's why this is slightly going beyond of that value, and this is equals to up to f prime x. And when we will be taking up to second order, then we will be going further downward, and that's why you will be getting 3 order values, which is close to the true solution. That's how, as much we go close to the as much we get higher order values, in generally speaking, we will be going closer to the original solution. And the conclusions we can draw from here that the more terms that are used, smaller the error. So if you use higher orders and truncate a less number of terms, then you will be getting more accurate values. Smaller the spacing, smaller the error for a given number of terms. So think about it. If that this interval, the spacing were not 1, rather it were, say for example 0.5, then for 0th order approximation, think what would happen. This would be the point for 0th order if the interval h were 0.5 instead of 1. the value will be there. This one will be the value, would have been this value for function of xi plus 1, and original value, original solution would be this point. So the error will be obviously less than the previous than the interval using 1. So that is the main consequence here. The smaller the spacing, the smaller the error for a given number of terms that I was intended to speak here. However, now there are two problems here for us which we'll try to solve, and after that we'll be concluding, giving concluding remarks for today's class. Before that, we'll be trying to solve these two particular problems. First problem says use the Taylor series. Use the Taylor series to approximate xi plus 1 using h equals to 1 and xi equals to 0. Compare your results and truncation error for 0th, first and second order approximation. Okay. To start this problem, before starting this problem, I would like to mention something. If I give you the derivative of f of x approximation, like this is the f of x approximation, which is we can approximate like function of x plus h minus function of x divided by h. And if I say that function of x equals to 7 epsilon e to the power 0.5x and h equals to 0.3, now I will be asking you to find the approximate value of function f prime 2. So as we know, the derivative approximation is this one, so it will be used for calculating this one. The true value of f prime 2. And also I will ask you to calculate true error of a. So as we have approximate this thing using the true value, you can calculate the true error. Also the relative true error. So I think you can easily calculate these things. I'm just giving some example. I'm just giving some key notes here. While calculating this thing, you'll be writing like f2 plus 0.3 minus f of 2. This is nothing but h divided by h. It will give you the answer as 10263. And this is a. While calculating b, you can easily calculate the true solution, how to get the derivative of f prime x d by dx of fx. Then you will be calculating f prime of 2 using the value 2 in this particular obtained derivative function, from which you will be obtaining the value as the true solution. This is the true analytical solution you will be getting as 9.514. Therefore, the true error will be 9.5140 minus 10.263, and it will be nothing but 0.722. And if you get this is true error, this is ET, and if we want to know the epsilon t, actually if we use percent before this, it will denote percent epsilon t. But if we don't use percent, this will indicate only the relative error. I can't remember what I have shown in the slide, but this is the actual thing. If it is percent included with epsilon t, that will indicate the percent relative true error. And unless we use, if you don't use percent, this will indicate the relative true error or relative approximate error in case of epsilon a. So in this case, this will be relative true error, which is true error divided by the true value. And we know the true value, also we know the true error, and from this we can easily obtain the value as 0.0758888 or whatever you say. Okay. And if we calculate it as percent epsilon t, where if we were asked to do, then we can just multiply this with 100%, which would generate the value as this one. This would have been the answer. But in this case, we don't have to do like that. The same problem I can ask you to conduct. This is the same problem. You will be first evaluating the f'2 using h equals to 0.3. In this case, no true value is given, or neither any true value is given, nor you are asked to do. So you will be only using the approximate value throughout this math, using h equals to 0.15. So for these two approximation, you will be getting the value, and then you will be calculating approximate error in case of part B. So for part B, if we say approximate error for part B, then you will be assuming this as the current approximation and this as the previous approximation. And therefore you will be applying the formula and calculating the approximate error, and also calculate percent relative approximation error. You can easily calculate this one as well. So try this in your home, practice this thing. I think you'll be able to calculate this thing. So however, I will be now moving to our main problem. The main problem was regarding the Taylor series, the question. Let's see whether we can import the question here or not. Okay, we have imported the question here, so we can move for the solution. So we will have to use the Taylor series to approximate xi plus 1 using h equals to I, okay, and xi equals to 0. So each iteration, it's adding up, each iteration will be adding up 1 here. So not necessarily, I have said before that this I plus 1, if xi equals to 0, not necessarily this xi equals to always 1. This is not necessary always. This 1 means the next step. If the h equals to 0.5, then if xi equals to 0, then xi plus 1 will indicate 0 plus 0.5. The next iteration, that will be 0.5. So this is the fact. So however, eventually the h value here is 1. Therefore, xi equals to 0 and xi will become 1. But it is not because this 1 is added. Just because this 1 means the h, one iteration will be added to this 0. That's why it has become 1. So please remember this thing while calculating. You will get confused, and I will try to confuse you in the exam. So please be careful here. However, the question is to compare your results. First of all, we'll need to approximate xi plus 1. Then I'll have to compare my result and the truncation error for 0th, first and second order approximation. So I will be taking only this one, then I will be taking this two, and finally I will be taking up to second order. Means this not like that actually. We'll be following the 0th order, first order and second order. That means will be, first of all, we'll have to take the 0th order, first order and second order approximation. So we'll be comparing it with the Taylor series, not we'll be taking the series like as I have said, just omitting the other one. Practically we'll have to compare it with the Taylor series. Okay, however, first of all, let's use the Taylor series to approximate xi plus 1. So how to use Taylor series here? First we will say, for the solution, I will say first that xi equals to 0, so h equals to 1, therefore xi plus 1 will be equals to 1. Then the Taylor series, according to the Taylor series says that if you want to calculate fxi plus 1, you will be, that will be equals to fxi plus f prime xi h plus f prime double prime xi h square by 2 factorial plus f triple prime xi h cube by 3 factorial plus dot dot dot. So this is our main Taylor series expansion. So whenever I have said that 0th order, first order, that means 0th order will be taking only this value. Second order, first order means only taking up to this one, and second order means up to this one we'll have to take. So that was our philosophy. So how to compare and how to merge the original, our main practical problem function, this function, into this Taylor series. Let's see how. Before that, if you want to get the error, the truncation error, obviously in this case you must need to know the true solution. The true solution might be given or also might not be given. If it is not given, you will have to calculate of your own by solving this analytically. So we will have to solve this analytically here. So what is our expectation? The true value of f0, first of all, we will be calculating, that is putting the value of x equals to 0. So it will be 0, 0, 0, 0, only 1.2 will be remaining. Okay, and when the true value, so these things we are calculating the true value, function of 1, when we will be calculating function of 1, we'll be putting here 1, 1, 1, 1, 1.2. So 0.1 multiplied by 1 minus 0.15 multiplied by 1 minus 0.5 multiplied by 1 minus 0.25 multiplied by 1 plus 1.2. It will be giving you the result as 0.2. So these two are the true solutions. This is function of 1, and this is we will have to calculate this function of 1 using the Taylor series, taking this one or this one or this one and compare the result with this one, so that we can obtain or calculate the truncation error, the error generated due to truncating the higher orders. Say for 0th order, say we only take 0th order. So if we just take the 0th order, then the function of 1 will become function of 0 from the Taylor series. Only this one will be taken for this. So this will become nothing but 1.2. So see the result. Original true value is this one, 0.2. And our approximation for 0th order says this will be 1.2, that is equals to this one. Huge difference. So according to the question, we are asked to calculate the truncation error. So truncation error will be actually the true error, so we'll better calculate the epsilon t here, percent approximate true error here, as we are comparing it with the true solution. That is, the formula was true value minus the approximated value divided by the true value. If we multiply this with 100% to get percent relative true error, it will give you a value of 500%. See, using 0th order, 500% of the error percentage. So now we'll be using for first order. For first order, the value will be function of 1 will be equals to function of 0 plus function of 0 multiplied by h. H means here we said that the question mentioned that h equals to 1, so we'll be taking 1 here divided by 1 factorial. So before that we'll have to calculate the f prime of 0. So how to calculate f prime? First of all, we'll have to calculate f prime of x. If you calculate the f prime of this one, this function, this one will be eliminated, only these portions will be remaining. After deriving, the x power will be downgraded to each x will be power will be lowered to 1 value, up to 1 power. So the value of function prime x will become, the power will become as a multiplier in front of each of these variables. So 0.4x cubed, 0.45x squared minus x minus 0.25. We'll get this sort of values from this one, derivating this thing. So if you use f prime of 0 here, we can easily calculate the value as minus 0.25. So the value for the first order f1 according to the Taylor series will be this one plus, directly put down these values, 1.2 minus 0.25, 1 factorial 1, it doesn't mean anything, so that's why it will become 0.95. Again, think about it. The true solution is 0.2. Previous approximation said this will be 1.2, which is very far behind the original value. This one is also far enough, but better than the previous one. But again, if we calculate the percent relative true error as 0.2 minus 0.95 divided by 0.2 multiplied by 100%, we'll be getting the result as minus 375%. Error has decreased. Now for second order approximation. In this case, we'll have to again differentiate the f prime x. So if you differentiate this thing, you will be getting the differentiated value, which will be minus 1.2 x squared minus 0.9x minus 1. So using f double prime 0, you will be getting the value as minus 1. So the Taylor series says in this case, function of 1 will be equals to function of 0 plus function prime 0 1 by 1 factorial f double prime 0 multiplied by 1 by 2 factorial 1 square by 2 factorial. So this will give you 1.2 minus 0.25 plus as we have obtained minus 1, so minus 1 into 1 square divided by 2 factorial. This will give you the value of 0.45. Now it is slightly improving, as you can see here. The value, my epsilon t percent will be getting 0.2 minus 0.45 divided by 0.2 multiplied by 100%, which will give you the error of minus 125%. Even this one is very large percentage of error, we can see, due to the truncation, and the truncation error is due to, as we have omitted these higher orders. As much we will be including these terms, the errors will be minimized and the result will be more getting closer to the original solution, that is 0.2. So finally we have found 0.45 as our up to second order estimation. So what we can do, we can create a table to summarize all these things, and I will personally, obviously I will always recommend to create tables I will personally recommend to create tables here all the time. So this is actually the table where you will be, here we will be giving the approximate order, there will be giving the true value, there the approximated value, and there that error we have got in percent. So 0th order, 1st order, 2nd order. The true value in all cases 0.2. Approximated value, first one was 1.2, second was we have found 0.95, and third one we have found 0.45 just now. And the percent error was like this. Finally we have found minus 125. So all this is the summarized answer for our particular problem. So now let's move to the next problem, after which we will try to summarize our lecture today. What does the question say? The Maclaurin series expansion for sin x is the following. Sin x equals to x minus x cubed by 3 factorial, x5 by 5 factorial minus x7 by 7 factorial. Starting from sin x equals to x, add terms one at a time to estimate sin pi by 3. Compute the true approximate percent relative errors at each step after a new term is added. Add terms until the approximate value of the approximate error false value and error criterion conforming to two significant figures. The two significant figures means indirectly we can say the value of epsilon s equals to 0.5%. According to the formula we have learned before, as you can see here, we have learned before the criteria, they are up to 2. This n value is 2 here, so it will eventually become 0.5%, we can say. Okay. So let's try for this. We'll be adding terms one by one. First we will be taking sin x equals to x. If we see that the error is not falling below 0.5%, then we'll be moving and adding x cubed by 3 factorial, then x5 by 5 factorial, until it falls below the error criteria. If it falls below the error criteria in this point, in this up to this term, then we'll say this is the answer, our satisfactory answer. We don't have to move further after this. Okay, so let's start the problem. Before that, let's see whether we can import the problem here as well. We are trying to import the problem here. Yes, now we can start. We can begin here. So first here we'll be assuming sin x equals to x. Our target is to calculate sin pi by 3. For that, let's use calculator, and the criteria says what it does. It says that approximate error. Just because of what? You cannot calculate the exact value of sin pi by 3. There is no exact value you can calculate unless you get the whole terms, all infinite terms of the sin x. So that's why approximate error. So each term is added, we will be comparing it with the previous approximation, as we don't have any true approximation here. Although still we can calculate the approximated true value using the calculator as well. The calculated approximated value will be like this one, 866. Don't forget to convert this into radian before, mode of radian into calculator, 25. So this will be like this one will be the sine pi by 3 using calculator. So now we'll be using first iteration, as we have said, sine x equals to x in first iteration. So sine pi by 3 will become eventually pi by 3, and this will be nothing but equals to 1.0472. So this is an approximation. In first case, there will be no approximated error just because there is no previous approximation before this one. So for the first iteration, we will not be getting any approximated error. So we'll certainly have to move to the second iteration for calculating the value one by one. Okay. What we have said to use epsilon s equals to 0.5, 10 to the power n means 2 minus 2%, that is 0.5%. If we find the value of epsilon a becomes false value or equals to 0.5%, then we will say the criteria is satisfied, and up to that term using which we have obtained this error, that will be our satisfactory result. So we don't have to move further after that. Okay. For the first point, we will not be getting any value. Okay. Let's move for the second iteration. And it also says the value, if the second iteration value becomes, say, second iteration will be automatically satisfied if the value of second iteration of sine pi is equals to, say, 1.04612 something. So this is up to 2 digit. If it is satisfied with the previous result, then we will say this is satisfied. Also, we can indirectly check this epsilon a whether it is equals to or below 0.5%. That will also say this is satisfied. So let's see what happens. In this case, second iteration will be adding up another term, that is x cubed by 3 factorial with the original value. So this is the case sine pi by 3 when we say this is x minus x cubed by 3 factorial, that is pi by 3 minus pi by 3 whole cube by 3 factorial. And from this, we'll be getting the value of 0.8558. In this case, as from the beginning I was speaking that in generally speaking, as much we will be using the higher orders, there is a possibility that the error will be deducted, but not always. This is because if you see this sort of example, this is actually derived from the Taylor series, but here is minus plus is there. There is a possibility it might be like for adding this term will be decreasing and adding this one will be increasing the value again. So there might be a possibility the error will be again increased in this portion when after we have added the third term with the second term. It is possible that after subtracting the value up to this term, the value was close to the original solution, but after adding a third term, it is again going, or it is diverted from the original solution. It is possible. So that's why I always say, generally speaking, that adding up a more term will be possibly it will be giving the more accurate results, but not necessarily. Even in this case also, not necessarily that minus plus always again it will divert it from the original solution. It is also possible that the original solution lies here. When we subtract it, it will become there. When we add things, it will become there. So it is going here, then it will going here, it will go there. So it is also possible that adding or subtracting it might also give the solution more close to the accurate solution. It is also possible, or also it can divert it from the original solution. So it doesn't matter, but I have just given a sort of examples why it might not always give the accurate result after adding the higher terms. However, sine pi by 3 up to second order, adding up second order, this will give this value, and from this you can easily understand that after a decimal point, two digits are not matched, neither these two digits are matched, nor the rounded value, the 1 is not matched with this one, as it is 0, you can see. So it will not satisfy after first iteration, and after this digit it will not be satisfied. Also, still then we can calculate epsilon a percentage using the current approximation of 0.8558 minus the previous approximation 1.0472 divided by the current approximation, that is 8558 multiplied by 100%. So it will give you a relative error which will not be less than 0.5%. You can calculate it of your own. Now the third iteration we are going for, and for this case sine pi by 3 will become x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial. And this case will be going for pi by 3 minus pi by 3 whole cube by 3 factorial plus pi by 3 to the power 5 by 5 factorial. One thing you can do is the result up to this term we have already obtained, so just add this value with the previous value, which will give you the answer like say for example this is it will give you 0.8, it will give you value of 0.8663, and in this case you see here this value is, the two digits are almost similar. Yes, it is similar. If you round it, almost similar but not similar, so that's why we can give a check here. Epsilon a percentage will be 0.8663 minus 0.8558 divided by 0.8663 multiplied by 100%. Let's see what is the answer. So this will be giving you 1.212% of error, which is not less than 0.5%. So criteria is not satisfied. Also the digits after digits is not matching up to 2 digits after decimal. So we'll have to move for the fourth iteration here. For fourth iteration, sine pi by 3, you'll be getting, I can say the value will be 0.8663 minus x to the power 7 by 7 factorial, that is minus pi by 3 whole to the power 7 divided by 7 factorial, which will give you the value as, and it will give us the value as 0.866026 like this. And from there you can easily see that the first two digits, not only 2 digits, up to 3 digits, it satisfies the result. So we can say up to this term it will satisfy our criteria. And also let's check the epsilon a criteria here. Epsilon a percentage will be equals to 0.866026 minus 0.8663 divided by 0.866026 multiplied by 100%. And let's see what is our result here. And the value we obtain here is very less than the stopping criteria epsilon s, less than 0.5%. Not only less than 0.5%, but also 0.05%, less than 0.05% as well. We are taking, this is to be mentioned that we are using approximate value, so this will become positive. However, this is also less than 0.05% as well, which indicates it is correct up to 3 digits, although our criteria was to calculate up to 2 digits. However, it is also it is not only fulfilling the criteria of 2 digits but also the 3 digits as well. So we will be saying that this is our desired result and this will be our answer. So that is our math problem according to this particular statement. Okay. The true error, although we say to calculate the true error, we can say that this is the true error, true value, as it was it is asking us to calculate the true value. Although we cannot calculate the true value here, just because we don't know the actual result. The calculator is not also giving us the accurate result, just because it has the limitation of digits in its screen. Just because we cannot calculate the true error like this. So if I give you a question, I will not ask you to calculate the true error for this particular solution. I will be asking you to calculate the true solution only if I give the estimation for, say for example, sine pi or sine 0 or pi by 2, if I say, where either 1 or 0 value will be there, the true value is already known. But unless it is known, I will not be giving you the question to calculate the true value, as you cannot calculate the true value from here unless you go up to infinite values, infinite digits actually. So however, this was our these two main mathematical problems, along with the other problems of approximated error or true error calculation I have shown here today for our class. Now I will be giving some finishing remarks before I will be discussing one or two few slides. See here, the total numerical error. The total numerical error is the summation of truncation error and the round-off error. And if I plot these two errors in the graph, most of the time we see that the truncation error increases as the log step size increased. If you take more size, if you get more step size, the truncation error will be the truncation error. This is the truncation error, and if you use the step size, if it is reduced, the error also increased. So this thing, if I want to describe it again, let's go for a demonstration. Say for example, if it is 3.0132, okay, and another is 1000.0132. So obviously the step size is a big factor here. If you see that if you take higher values, that is if we take very large step sizes in case of errors, then the round of errors will become minimal. That is, if we take large step sizes, for example, we have taken large step size h equals to 1, h equals to 2, instead of h equals to 0.25. So when you will be taking large step size, in those cases the round of error will become less significant. It is true, just because already this higher order, step size will result in big amount of error. So the round of error will become less significant in these cases. Forget about this example. But if we take less step size like this, in that case the error will be will be minimized, and the value will be trending to become close to the original values. And that's why in that case the round of error, if you just round it off, in that cases if you round it off in 2 digits, then it will be very much significant compared to the round off in 2 digit in cases where the step sizes was 1 or 2. In that cases the values you have obtained, like say if I give example, this is the true value. When you use step size of 2, your value becomes 5.01 32 like this. So it doesn't matter whether you take this value up to 2 digits or 3 digits, it doesn't matter. But when you take less amount of step sizes, then your approximated value will be like 3.0352. In that cases, obviously this 0.32 digits is obviously significant for you. So that in that case round of error might create complexities for you or generate higher errors, percentage errors. Whereas in case of higher orders it will less likely to be governed here. Again, in case of truncation error, what will be it will become? In case of truncation error, as much we will increase the step size. If we take higher order of step sizes in case of truncation error, say for example these things, in these cases if we use higher step sizes, the truncation error will become what? Whether the truncation error will be minimized or increased, what will happen? If we take large step sizes for truncation error, say I mean that for the Taylor series, if we review the Taylor series again, this thing. So if we take higher order h values, this step size is high, say this is 2. What will be the result for this? If you take the same amount of terms, and if you take h equals to 4, what will be the approximated error resulting from this? Obviously, if you take larger values of step size, it will generate more error. As much the step size is smaller, the although we are taking up to 3 steps, it doesn't matter. But if the step size, if we take up to 3 terms, it doesn't matter. But if we take smaller step size, that is h equals to 2, then certainly it will generate less error, and it will be more accurate if we compare it with the h value equals to 4. Obviously h of 4 will be giving more errors, and h equals to 2 will be giving less error, and it will be more closer to the original solution. That is our concern here. So that is the thing what we have concluded here in this particular graph. So truncation error will be increased with the step size, and the round of error will be decreased. Our target will be the point of diminishing returns, where these two intersect. This will be the minimum error. So we want to reduce the total combined error, and our target will be this one. The total error will be diminished here. So if we can find this one, that is our success, and this is the more accurate result we can generate, we can obtain from our particular problem in the numerical analysis. So this is the last slide. There are other errors as well. First, we can say about blunders, that is the errors caused by malfunctions of the computer or human imperfection. That is if you yourself make any mistake or in computer algorithm it becomes any problem, so it cannot approach further according to the original technique, and it will generate some errors, that is called blunders. Model errors resulting from incomplete mathematical models. So if my technique or model basic fundamental formula becomes obsolete, then this model errors will become visible in front of us. And data uncertainty is the error resulting from the accuracy or precision of data. So we will learn about this thing, that accuracy and precision, these two things are not same. Accuracy is different and precision is also different. So however, data uncertainty, if you do not have the accurate data, it will obviously generating the error in the model. So say for example, in case of Bangladesh and third world countries like us, where the data uncertainty is very much visible or apparent, there we will face this kind of problems. So we don't have the original data, and that's why the model or numerical method technique after application, what we are getting the result, say for example the COVID data or other data, what we are getting, we cannot rely on these things just because of what this data uncertainty. So how much your numerical analysis is precise, it doesn't matter, but as the data is uncertain, so your result will be also uncertain as well. So these will also generate in errors. However, so this was our first lecture, so I don't want to talk further, so I will be finishing it off. Hopefully I will be giving the assignments to you. You will have to submit the assignments regularly, and regularly you will have to get prepared for any kind of quizzes. It doesn't matter whether we are conducting the classes in online or offline. It doesn't matter. You will have to be prepared with your answer scripts, quiz answer scripts, which if I give you questions in 5 minutes within, you will have to solve and capture the picture and upload it in the classroom, where it will be the assignment will be generated. However, I will give regular assignment after each class, so you will have to regularly submit the assignments as well. So thank you for being with us today. Thank you everyone.